actually here 3 sets of hinges will form. First, the shortest pier will yield, hinges will form at top and bottom. Then the left pier will develop, the mid height which is having high intermediate height, that will yield at top and bottom, and then the tallest pier will yield at top and bottom. So what you get? V1 and delta 1 at first step by equating maximum DCR equal to 1. I have given same. What's the problem if I give same? Why? I am making a bridge in which all the 3 pier sizes I have kept same. I have only varied height. Stiffness will not be same, EI will be same. So I have not said stiffness is same. I have said EI is same. Do you want your stiffness to be same? You can decide. You are making bridge. You can make anything.
No. It's a concept.
You can make stiffness same. In that case, this will have larger dia. Okay, its EI should be larger. This will have a smaller dia.
I thought that you were asking in general what should be.
So you are a designer. You can design anything. I have designed this in such a way that EI is same, L is different. Whether my design is good or bad, that we will see later. But at the moment, I have designed a bridge, I have provided same EI. We will discuss. If this type of design I am doing, what are the problems? V1 will be
V1 into 2n by 2.
Huh.
Or I will calculate for
No, sorry, I couldn't get.
for DCR1 capacity is V1.
No, this is okay, but V1 you have to replace in terms of V. Now, finally, you can compare. Till these are different, V1, V2, V3 are different. You can't say which one is higher. So everything has to be converted into same. So V1, V2, V3 you have to calculate in terms of V. And for that you have to use compatibility. Displacement has to be same. So when this is deforming here, this is deforming here, the displacement is same. So that condition you will use to get V1, V2, V3 in terms of V. The total force acting is V, which is equal to sum of these, and V1, V2, V3 you can obtain in terms of delta. So V1 is 12 EI by 2L cube delta. V2 is 12 EI over 3L cube into delta. And similarly V3. And then V1 plus V2 plus V3 is equal to V. So you can get V1, V2, V3 all in terms of V. Substitute that, then you will get the maximum DCI.
So hinges are forming here. Here and here simultaneously.
Okay.
Q1 equal to correspond 108 over 251. Yes.
108 over 251 L.
Ah, yeah.
108
Ah.
M
Divided by 251 L.
251 L. Okay, good. And how much is the corresponding delta 1?
No, sir. This is 251 over 108.
Full time?
251 is simply
ML square over 6. Now what will happen? In step 2, so there will be only two columns to register the load in step 2.
what was the D in the first step?
251 M by 108 L. This is, let me call V superscript 1.
To cause first change. This is the force.
When the first set of hinges is forming, and first set of hinges is forming in the shortest pier at top and bottom simultaneously.
Total base shear required for this structure.
Total base shear required for this structure. Yes. Right here. You will take this assembly, plot its Q versus delta. Q versus delta, not 3Q versus delta. So for each assembly, you will first obtain Q versus delta. Then combine those for every assembly. First you plot Q versus delta. Then combine the assemblies of a story to get V versus delta, where these curves will be combined, not Q. Curves will be combined. And how to combine the curves? I have given them. Okay. So don't think that you have to apply this force. That it is one way of looking at the problem. Other way of looking at the problem is that I know Q versus delta for each assembly. I will combine those. So there we are starting from the assembly and then coming. You are more habitual to look in terms of distribution of the force. Sorry. No difference. Only difference will come when it will be be combining the stories in series. Their base shear will be equal to Q. Here the base shear will be 6. So this difference will be there. Otherwise, in the procedure, note here also you will first calculate Q versus delta, 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 and sum of these two, sum of these two, sum of these. Here you will first take this force. At that force you will calculate how much is the shear at other end. This is in terms of force. In series, the force will decide, not the distance. You will take a given force, you will read displacement from different curves, and you will add a displacement. So whichever the story is having, whichever is yielding earlier, that story will be. And it is not necessary the story which is having lower yield force will yield first, because it will depend upon the shear also. Let us say the ground story is having 5 times the story shear. Okay. Top story is having, let us say, 100 kN, or no, this is 2 kN. 3. So let us say top story is having 3000 kN, and this is having 4000 kN. Which one is going to fail? 3000 or 4000? Why? Because the applied force is 6 times here, and here it is 3. So that's why this ratio becomes 6. That will decide that which story will give you the first yield. We will discuss at what point to focus. We can discuss that again and again, as many times you want. Okay, so I guess you can complete it now. Okay, you can do that. You can complete it at home, I mean in your hostel. You can do that. Now, the question I wanted to highlight was this. Here, if I have to plot V versus delta graph, how I am going to plot in this case? What is the problem? What is the difference as compared to the previous one?
Your delta will not be same.
Delta will not be same. Okay, so you cannot combine. So what we will do here, we will plot separate V versus delta for each pair. So here we will make pairwise model. Okay, so you can make a pairwise model in this case, and this is one pair. You will have the mass. How much is this mass which we will get? In the longitudinal direction, let us say this is W1, this is W2, and I am considering this pair. So in longitudinal direction, how much will be the mass?
W1 by 2 plus W1 by 2.
In longitudinal direction. So when it is vibrating, will W1 will act on this pair or this pair, or half on this pair or half on this pair? One end is spin, other end is having roller. So where this mass will be acting?
Half.
Simply supported, half is the vertical reaction. We are not talking about vertical reaction, we are talking about horizontal mass. So in the longitudinal direction, it will be W2 by G, because I am calling it mass.
How mass can act in non-linear direction?
Mass can act in any direction.
Yes.
So how much mass is effective in horizontal direction, that we want to know.
But how will you get that?
You will get that. You try to shake it. Okay, when you are shaking it, you will get some inertia force.
Yes.
So what is mass? How do we define mass? Mass matrix we have derived. So what is the definition of mass? Mass matrix is also Mij. No, it is not always diagonal element. There are cross terms also. Mass matrix is not always diagonal matrix. You have heard consistent mass matrix in finite element. So their non-diagonal terms are also there. So mass can also be Mij. So what is Mij? How to define Mij? Like Kij you have defined. How did you define Kij? Kij, let us first do. Force required along I to cause unit displacement along J. Same way, define Mij. Force required along I to cause unit acceleration along J. So inertia force which will be acting at ith node or along ith degree of freedom when acceleration is acting along jth degree of freedom. Okay. If you are considering diagonal, then it will be only Mii. So wherever the acceleration is acting, inertia force will act. Okay. So here if you apply acceleration, where the inertia force will act. Suppose the whole structure I am moving with an acceleration A in this direction. So where the force will act?
Seizure of mass.
So it will act W1 by G into A here and W2 by G into A here. Where will this force get transferred? Will it act here? No, because this side is roller. It cannot take any force. So whole of this force will get transferred here. So this will be W1 by G into A. How much will be the force here? W2 by G A.
Last year will not face any last year.
There is no, actually there will be another, I have not shown that here, but there may be another superstructure here till abutment. But whatever is at the end, it will not have any mass. So if you are having arrangement of the superstructures bearings like this, pin, roller, then at the end you will have roller, and that will not have any force in the longitudinal direction. I have not yet talked about transverse direction. We are talking about longitudinal direction. In longitudinal direction, that abutment is the end support of a bridge. So that abutment which is having roller support will not have any inertia force due to superstructure along longitudinal direction. Okay. But what will happen in the transverse direction? These rollers are in the longitudinal direction. In transverse direction, what happens? In transverse direction, when this is acting, 50% of that will act here, 50% of this will act here. Similarly, 50% of this will act here, 50, half of it.
Sir, you are giving acceleration to the middle tier, right?
No, we are giving acceleration to the whole structure, not to a particular pier. We are giving acceleration to the whole structure. You agree? Half or half will act here, or it will act in proportion to the stiffness. Will it be in proportion to stiffness, or will it be half? What do you think? Half, not in proportion to stiffness. In the transverse direction, one span is supported at 2 points. Okay, and I am giving acceleration, let us say, in the transverse direction, A. So each girder at the top, each superstructure will be subjected to W1 by GA and W2 by GA, where it will be transferred. In the transverse direction, it will be transferred on both the sides, both the supports. Will it be equal, or will it be in proportion to stiffness? Not in proportion to stiffness. Earlier you have said that, here you have said that it is proportional to stiffness. Here you are saying that it is equal.
Sir, in that the superstructure is connected with a rigid junction, but here it is supported on only on 2 points. So at the 2 points, the mass will be divided into 2 parts.
Moment is not transferred. So
Why will the column stiffness will be low?
suppose is any moment being transferred here? Suppose I put a load here. Suppose this are K1, K2, K3. Will the force be distributed uniformly in these 3 springs? How much will be the force acting in each spring?
Proportional to stiffness.
Proportional to stiffness?
Yes.
What will happen in this case? Will it be proportional to stiffness?
Yes, it is the same thing. Yes.
Same thing here. So this will be in proportion to stiffness. So why you are not saying proportion to stiffness here? So keep in mind, there is no rule which says that the force will be distributed in proportion to stiffness. What is the rule? The rule is compatibility and equilibrium, only those 3 equations. So both your questions are wrong. Sorry, both your answers are wrong. This will not be proportional to stiffness. Suppose K1 is 100 kN, this is 50 kN, this is 25 kN per meter. So what will happen? It will deform like this. The deformation will be, this side will deform less, this side will deform more. You agree? Load is applied uniformly at the top, so wherever the stiffness is less. When it will be proportional to stiffness, there is a special condition. And what is that special condition? That the displacement should be same. Then only. You have seen that in case of building in the last semester also. In case of a building, when the base shear is distributed proportion to the stiffness to different frames, when the building is not having any torsion, it is having symmetry. So suppose these springs are symmetric. If you have this type of springs, (100 kN per meter, 50 kN per meter, and 100 kN per meter, then it will be proportional to stiffness. But not here. Here it won't be proportional to stiffness because the displacement is also changing. Okay? Are you getting this simple study? All of you have done that. What will happen in this case? Suppose this is 100 and this is 50. Kilometers per minute. What is going to happen here? Again, this will deform. What will happen to the force? Will it be same or different? Suppose you have to calculate the forces here. F1, F2, F3. How you are going to obtain? Can you obtain these F1, F2, F3? I gave you this problem. A very simple problem. How you are going to solve?
Equilibrium equation and comparative equation.
Equilibrium and comparative. These two equations you will satisfy. Use this, let us say this weight which you are having here, that is 1000 kilonewton. Stiffness is 100 kilonewton per meter and 50 kilonewton per meter. Solve and give me this F1 and F2. You will find something very interesting. Do that. See how? Moment about? But here the displacement is more, here is the displacement is less. So how do you justify that?
Because but K is also different, no?
Yeah.
Automatically adjust. K will be
Do it. I want you to do it. That will be better. Please solve. Use equilibrium and compatibility. And constitutive law. What is the constitutive law? That F1 is K1 into delta 1 and F2 is K2 into delta. These are the constitutive laws. So assume delta 1 and delta 2, calculate delta 1 and delta 2, and then you will get F1 and F2. What is it?
Force remains same and the stable by the stiffness and weight.
So the displacement will adjust in such a way that the force remains same. Force has to be same. Why force has to be same? From the equilibrium condition. What is the equilibrium condition? That moment about any point has to be 0. So suppose I take, this is the applied force of 1000 kilonewton W. I take moment about this point. So you can see that this is L by 2 and this is L. So I will get the value of force here. I take moment about this, then this will be L by 2, this will be L. So if I take about this, I will get this. If I take about this, I will get this. Both will come out to be the same. So forces will come out to be the same in this case because of equilibrium condition. Okay. And if the forces are same, the displacement will adjust in such a way that the displacements into stiffness are giving you the same force. So the displacement at the two springs are going to be different. That will happen only when there are two springs. Okay. If there are three springs, then you can see that if you take equilibrium about any of these points, you can't say that both forces are equal. Only if there are 2 points. So if any member is supported or it is simply supported at 2 points, the forces will be equally distributed even if this is inclined. So even if this is inclined, whatever force uniformly you are applying on this, it will be distributed equally. So now you can understand what is going to happen here. If I apply inertia force in this direction, how much inertia force will be transferred to the central pier in the transverse direction? In the transverse direction, it will be W1 by G by 2 plus W2 by 2G into A. So this is going to be my mass in the transverse direction. Okay. So I can develop separate capacity curve for these piers, but these capacity curves, okay, I have to keep in mind that the mass is going to be different. Have we considered mass anywhere so far in our capacity curve? No. So this will come into picture when we will trying to get the response. So suppose this is circular, this pier is circular. Okay, circular means in the longitudinal direction and the transverse direction capacity curve will come out to be the same. Okay. Still, its response will be different in the longitudinal and transverse direction because the masses are different. And what will happen? The central pier is most flexible and it is subjected to larger force also. So the central pier is going to vibrate more. So in the superstructure, you will get a torsional motion. In the longitudinal direction, it will go in the line, but in the transverse direction, the central pier is going to move more. The end piers are going to move less. So there will be a torsional motion in the superstructure also. Okay. We usually ignore that torsional motion. If I want to consider that torsional motion also, then I have to make a full model and I have to perform a dynamicity analysis. But we do a simplified model where we separate these piers and we develop capacity curve for each pier separately. There it will be just acting like a cantilever column. Okay. So if the bridge superstructure is simply supported, then capacity curve is very simple. It is like cantilever. Okay. Sometimes the piers are also framed. We have framed piers. In framed piers, what we have? Let us say this is one pier. We have another pier. And then we have the superstructure. Over there. Okay. So we can have framed piers also. And this may be simply supported. The superstructure may be simply supported on these frame piers. If I draw this, it will look like this. I will have pier. At the top of the pier, I will have bearings. And then I will have superstructure. In this case, what will happen? In the longitudinal direction, each of these piers will act like cantilever, okay, consisting of these two columns. In the transverse direction, it will act like a frame. Okay, you might have seen this type of piers of the bridges also in some photographs. So in the transverse direction, this will act like a frame. In the longitudinal direction, what will happen if I am applying a force in the longitudinal direction? Then what is going to happen? This will just act like a cantilever. So you can obtain the capacity curves of any pier superstructure arrangement. Okay. Superstructure does not have much role. Okay. In case of simply supported bridge, it is just acting like a mass. And in case of a continuous integral bridge, it will act like a rigid beam. Okay. Here, in case of bridge, the hinges are formed in the substructure, in the column. Okay, there is a difference. In case of buildings, we have designed those in such a way that the hinges should form in the beams, not in columns. But in case of bridges, the hinges form in columns, piers, not in the superstructure. Okay. What implication it will have if the columns are having hinges, not the beams? What effect it will have on the seismic behavior of these structures? First of all, can we have hinges in superstructure? Why not?
Declinal structure, bridge, simply supported. If hinge in form, it will fall down. Right. Single hinge will collapse the structure.
So we can't allow a hinge at the midspan, then it will become a mechanism. At the end, moment is zero, so hinge cannot form. If suppose it is integral, this type of case, then it can happen.
Yes.
So any problem here? If the hinge form on the superstructure?
Serviceability. Serviceability.
Serviceability. Okay. What do you mean by serviceability? What problem?
Position may be more deflections due to
More deflection.
if plastic hinge will form there.
So first of all, superstructure is to be always designed for vehicular load. Okay. Vehicular load is not heavier than the superstructure itself, but it is much heavier than the load which we are having on buildings. Okay. If I bring a truck in this, what is your estimate? Suppose I bring a truck here. Will this slab be able to sustain that? What do you think? Suppose there is an emergency, I have to bring a truck, and you are a postgraduate, you have to tell whether that I can bring truck here or not. What do you think? What is your estimate? Will it collapse under truck? What do you think?
Yes, sir, we can say that.
आ जाएगा? You will allow truck.
No.
हाँ.
It will collapse.
It will collapse.
Because point load is acting on some area. The load is very heavy. And this slab is not designed for that.
So if I design the slab for that loading intensity, it might be able to.
Slab is in front of you. That is, this is 150 millimeter thick.
So whatever they will
Tell me whether truck can come here or not.
So I have.
Okay, think. You know how much load is in garages and parking? You have seen multi-story parkings also, no? So multi-story parking, cars can go. Can the truck also go?
Yes, it can go. If I have to park up there, then I have to design for that.
So will the design be different? Are you going to have larger thicknesses? How much large thicknesses
No,
will
the
you
load
generally require when you are designing those as multi-level parking? You can see now multi-level parking are everywhere. Next time when you go, try to see the thickness of the slab. How thick slabs they are requiring, or the thickness of the bridge. There are slabs on the bridges also. Okay, try to see the thickness. What thicknesses they are providing, and you will find something interesting. Okay. Let's come back to this. So there is load and spans are very large. So due to this heavy load and large spans, superstructure is generally very strong. Okay, it has lot of inherent strength and it can't yield. But if it yields, okay, then there will be shear failure. If the hinges are forming here, superstructure is yielding. Okay, so there will be shear failure, which we do not want. So superstructure we do not want to yield in case of bridges, and usually it will not yield. It will have so much inherent strength because of the gravity load itself that it is not going to yield. And in simply supported superstructure, there is no case in which it is going to yield because moments due to earthquake are not developing. It is just moving like a mass. So the plastic hinges form, the yielding occurs in piers in case of bridges, and it is contrary to buildings. What implications it will have towards the registers, seismic registers of these structures? Let's say in terms of response reduction factor, what do you think? What will happen to the ductility if the hinges are forming in columns?
Ductility would be more.
Ductility will be more if the hinges are forming in columns. Why you say so? Then we should allow plastic hinges to form in columns in buildings also?
No, at the bottom of the column. If the hinge is formed at bottom of the column, then we get large deformation. So ductility will be more.
So then why we are saying strong column beam design in buildings?
But there also we are forming the plastic hinge at the bottom of the columns at last.
That is at the end.
That
If hinge at the bottom is so nice, we should do it in the beginning itself. So hinges, I told you, hinges in the column, we want to avoid. Okay. At the end, it is not possible to avoid. Finally, when all the beams have yielded, finally the columns will develop so much moment that I can't avoid it. That's why we have at the base of the column. But I do not want in the column. And the reason is,
Period because the period addition that is already.
So P delta effect will be in any case, even if the hinges are in the beam, if the displacement is occurring, P delta will occur. So why we do not want in the column? I have repeated this several times.
Because of the actual force, ductility will be less.
Because of the actual force, the ductility will be less. And if the ductility is less, in bridge also, the actual force will reduce the ductility. If ductility is less, what will happen to the response reduction factor? R is equal to square root mu minus 1 or R is equal to mu, depending on whether it is short period structure or long period structure. So if mu is less, R will also be less. And that's why the response reduction factor of bridges are less than response reduction factors which we use in buildings. So bridges are designed for lesser response reduction factor. Okay. Because as you said earlier, these are determinant structures. Are these determinate structures which I have plotted here?
This one is not.
It is in the transverse direction. Okay. What about this one? Is it determinate structure? It is determinate, it's straight. In longitudinal direction. Okay. So in most of the cases, not all bridges, suppose you have an integral bridge with multiple columns, then it is not determinate in any direction. Integral, so in the longitudinal direction you will get framing action because of the superstructure at column. In the transverse direction, multiple columns. So that will not be determinate neither in longitudinal nor in transverse direction. But most of our bridges will be determinate either in longitudinal or in transverse direction, or in both. Okay, simply supported circular pier or rectangular pier, single pier, that will be determinate in longitudinal as well as in transverse direction. Okay, so first of all, these are determinate. Secondly, hinges are forming in columns, so the ductility is less, ductility is reduced, and if the ductility is reduced, the response reduction factor will reduce. Okay, so that's why if you compare the codes of bridges and codes of buildings and compare response reduction factors there, okay, the response reduction factors for bridges are much less, not more than 3 in any case. Okay, generally of the order of 1.5 to 3, that is the order. In case of buildings, what is the order of response reduction factor? 3, 4, 5 and 8. If you look at SC7, SC7 allows the response reduction factor of 8 for SMR. So response reduction factors in case of buildings are much larger because their hinges can be accommodated in beams, but in bridges the hinges will form in column. That's why the response reduction factor, ductility and hence response reduction factor are much higher. Okay, so now you can plot the capacity curve for any bridge. You think different types of bridges, try to plot capacity curve. Any question, discuss it, including the one which I have given in the assignment. Okay, one more type of structure I want to discuss. We have discussed frame buildings, we have discussed bridges. One more type of structure I want to discuss, and that is masonry buildings. How to develop capacity curve of masonry buildings. Okay, you have, some of you have done a course or are doing a course on masonry buildings. So a typical masonry wall is like this, and in plan the masonry building may be like this. Here I am having door, here I am having window, here I may be having window, here I may be having a window, and here I may be having a window. So either a wall will be like this in this case, or it may be like this, or any other combination of doors and windows. Okay, and in your masonry course you are calculating that if you apply a force Q here, okay, how much will be the force in different piers. The most critical section is this one. Why this is most critical? Because below this you can see that larger cross section is available. Above this also larger cross section is available. Okay, so most of your deformations and failures will occur here. These we call piers. Okay. So have you done in masonry how to calibrate stiffness of a wall, combining piers in series and parallel? You have done that? Okay. So what we do there, we divide it into number of piers, and usually this also we assign a pier. So let us say this is pier number 1, pier number 2, pier number 3, pier number 4, and pier number 5. Okay. So you can calculate stiffness of individual piers and represent them by a spring, and you have a spring analogy. And as per that spring analogy, the pier 1 is having a stiffness, let's say K1. Okay, then we have pier 4 having a stiffness K4. Then we have 2 and 3 which are in parallel. And then we have pier 5, and here is my force pier. So if you solve this spring arrangement, you will get the forces. In these piers. You agree? This arrangement I have shown, K2 and K3, pier 2 and 3, these are in parallel. You agree? How we decide? Again same, if the displacement is same, you can see that the interstory drift is same. But 1, 2 and 3, the drift is not same because 1 is connected here. So 2 and 3 and 4. 2 and 3 in parallel, and that combined with 4 is in series, and this whole is in parallel with 1, and then 5 is in series with this. Similarly here the piers will be like this. One, 2, 3 and 4. Can you draw the spring analogy diagram for this wall? We have K1 and K2 acting in parallel, and then here we have K3 and here we have K4 which are in series, and here we have this force. So like that you can develop an equivalent spring system for a wall. Okay. You can calculate the stiffness of the wall provided you know the stiffness of individual pier. Okay. So you need to know stiffness of each pier. So here, if you look at these piers, can you calculate the stiffness of these piers? First of all, see what will be the deformed shape. So this pier is going to deform like this. And this pier is going to deform like this. And this pier is going to deform. Similarly, these piers, this is also, although the deformation in pier 4 will be much less. Why it will be much less? Because moment of inertia will be how much? It will be thickness, let us say thickness is T, and this length will come into picture. So moment of inertia will be T into L cube by 12. If this L is large, the moment of inertia will be very large. So the deformation here is going to be small. Here the lengths are small. So that's why most of the deformation will occur in 1, 2 and 3. 4 and 5 you may or may not consider. The deformations of 4 and 5 you can even ignore, because the deformation of 4 and 5 is much smaller, or stiffness of 4 and 5 is much smaller. Now compare this 1, 2 and 3 with the RCC beam, which you have already done. So we have plotted, or we have obtained the stiffness of this beam. Now I have a pier which is also deforming like this. You know the relationship between Q and delta in this case. So Q is equal to suppose here what will be the relationship between Q and delta here? Same, plus what? What assumption we have made here? We have ignored shear deformation. Here you can't ignore shear deformation. So this delta here will have both the flexural component and the shear component. How much is flexural component? Which is coming from here. That will be how much will be shear component? How much is shear deformation in this case? QL by G. What is this AR? How much will be this in this case? Suppose thickness is T. This height is L. Okay. Rather, I will use this as H, and this I will use L. Okay. So I is how much in this case? TLQ over 12. And how much is AR? AR is A over roughly 1.2 or to 1.5, that factor is there. So that is T into L over 1.2. Let's convert G also in terms of E. Let's take nu is equal to so how much it will be in terms of E? Yeah, 1.25. So 2.5, 2.4. So delta you can write as QHQ over E T LQ, okay, plus 1.2 QH over 0.4 E into okay. Q okay, H I will keep inside over E T I take outside, so it will be H by L Q plus 3 times H by L. You might have derived this already in your masonry class. Okay. This gives you the stiffness. Up till this much, what you have already done in your masonry class. Those who are doing masonry course, they have done it. Okay. We will go one step further. This is giving us the linear behavior. So if I plot the relationship between Q and delta, let us say this height is H1, this height of the window is H2, the force applied here is Q, this is L1, this is L2, this is L3. Okay, I am plotting Q versus delta. When you apply this Q, this is going to be formed. Okay, let us assume that this and this are rigid because their length is much larger as compared to the other peers. So let us ignore the deformations occurring there. Okay, so you can see that initially it is going to be a straight line. Can you tell me what will be the slope of this straight line? That is the stiffness K.
So we are assuming this K4 and K2 and K3 are in parallel or series.
K2 and K3 are in parallel, and this parallel assembly is in series with
So
K4.
the deflection for both of these will be same for K4 as well.
No? When these are in series, force is same, not the displacement. Displacement of suppose I have K2 and K3 here, and I add those with a very rigid spring. What will be the stiffness of this system? Can you tell me? This K tends to infinity, and K2 and K3. So let us say this is our K4, and this K4 tends to infinity. I assume this to be infinite. What will be the stiffness of this assembly?
K2 plus K3 infinite plus something.
Infinite?
Infinite.
करके देखो.
Infinite plus something equal to infinite.
In series, are we adding the stiffnesses?
No.
So it is not infinite plus something. What will be the stiffness?
K2 plus K3. K2 plus K3 plus 1 upon infinity.
How much will be? Obtain here. Tell me after doing it. How much will be the stiffness of this assembly? First add these two in parallel, replace them by some K equivalent, and then K equivalent and K4 is in series. What do you get? K2 and K3 are not in series. K2 and K3 are in parallel. So first determine. So this is equal to this K4 plus this. So K4 is here, and in series it is having K2 plus K3. How much will be this stiffness? One upon infinite plus 1 upon K1 plus K2. 1 upon infinite is how much? 0. Okay, so it will be 1 over K1 plus K2. So it will be K1 plus K2. So stiffness of this is same as the stiffness of this. Okay. So actually the stiffness of this whole wall, if you assume this K4 and K5 are very large, if these tends to infinite, only in that case the stiffness here will be all of you agree? It will be K1 plus K2 plus K3. Because whole of this assembly is in series with K5. So if you add infinite stiffness in series, it has no effect. If you add 0 stiffness in parallel, it has no effect. Okay? But if you add 0 stiffness in series, what will happen? You add a very flexible element in series, what will happen?
The
Whole assembly will become very flexible. Okay. So if you add zero stiffness in series, whole stiffness will become zero. If you add zero stiffness in parallel, it has no effect. If you have infinite stiffness in parallel, the resultant stiffness will be infinite. Okay. So using that, you can see that K1 plus K2 plus K3 is the total stiffness. So actually the stiffness or the deformation is contributed by these piers only. Okay. The contribution of these piers in deformation is negligible, which we are ignoring. So I can write this Q versus, I can plot this Q versus delta curve for my wall very easily like this. Okay. Till when it will continue? What is going to happen if I go on increasing this force Q? Can I go on increasing it up to infinite? What will happen? In the first semester, we have discussed failure modes of masonry buildings. Okay, so some failure will occur. What type of failure? Which failure modes you remember? In how many ways the masonry wall can fail? In plane and out of plane. Here we are applying in plane force. We have not applied out of plane force. So it can fail in plane. In plane, how many modes? In how many ways it can fail? You have seen, in fact I have also shown you photographs of failure of masonry buildings. You might have seen a lot of photographs in which the masonry walls have failed. So what are the different modes of failure? Diagonal tension. What is that? How will it look like? If a building is failing in diagonal tension, how will it look like? Can you plot?
The cracks will start from and corners of the four walls and in between middle.
So this is diagonal shear failure. So diagonal shear failure is one mode of failure. Masonry piers. So one mode of failure is diagonal shear failure. And why it happens? Suppose I have a pier which has lesser height but larger length. So h by L is smaller. Then what will happen? If you apply a shear force here and a vertical load here, okay, a shear force and this will act, and there will be complementary shear and the failure will occur along the diagonal. Okay, so this is our diagonal shear. Another type of shear failure is also possible, in which when I apply the shear force here, the sliding occurs and it fails. This is sliding shear. Can you guess in which case sliding shear will occur and in which case diagonal shear failure will occur?
If the lower part is rigid.
Lower part is
Rigid.
rigid.
Ah.
Means lower part base neither it is moving here nor it is moving here.
That base you have shown, if that is rigid. And
It is in both the case it is rigid.
Bond used.
Bond means bond is on both masonry are same bond. So masonry is constructed using the same bond in both the cases.
If the shear area is less or
See, here it is sliding friction coming into picture. So when the sliding friction is low, I have intentionally not shown a vertical load here. So if the vertical load is small, okay, then the friction resistance, because the resistance here, that is equal to mu r. So if the vertical load is less, okay, then sliding shear failure can happen. If the vertical force is large and you are applying a shear force also, in that case diagonal shear force sliding cannot happen because mu into r is much larger. In that case diagonal shear failure can happen. But for both of these, the height to length ratio has to be small. The aspect ratio has to be small. On the other hand, if you have a slender pier, what do you expect here? Okay, and crushing will occur. This is called rocking failure. It is similar to bending. So these are the three common types of failures when H by L is large, aspect ratio is large. Then rocking failure. You look ASC 41. The chapter numbers have changed now, I do not remember, but you can look the masonry chapter there. There expressions, the formulae for calculation of capacity in shear and rocking are given. Ductility in shear and rocking is also given. Okay, so please look in ASC 41. It gives you the Q versus delta curve for masonry also. Okay. And this is the strength Qy. Qy will depend on rocking or shear. And accordingly, this D and this E is also given. Earlier it was A and B. Here it is D and E. Do you see any difference in this diagram which I have plotted as compared to the earlier diagram where I have shown A and B?
Yes, sir, it is starting from the ordinate.
Right.
It is starting from the right.
So the D and E which are given in SC 41, those include elastic deformation also. Whereas A and B which were given there for RCC, those were giving only plastic deformations beyond E. Okay, that's why a different notation D and E is used, not A and G. So you can see the values of D and E from ASC 41. Okay, once this backbone curve, okay, is available for pier, can you give me Q versus delta for this wall? Can you give that? How? You have to simply add them in parallel. How to add them in parallel? I have told you. For a given displacement, you will take one displacement, calculate the forces, add the forces, then take another displacement, add the forces, go on plotting. That will give you the complete Q versus delta curve for the wall. Okay. Same procedure we will use as we have done earlier. Okay, so this completes your tutorial number 3 also. So please attempt tutorial number 3 also, and whatever difficulties you have, because I am going to ask tutorial number 3 also in the exam. You are not submitting, or if you want to submit, you can submit. It's up to you. But it will be asked in the exam. So look at tutorial number 3 today, and whatever difficulties you have, we will discuss. It is very small and simple. Okay. It will not require that much effort as it was required in tutorial 1. Okay. A small question, and because it is a small, it has more chances of being asked in the exam. So please do it and discuss with me tomorrow. Whatever. Only one thing I want to tell you, and that is the concept of overstrength, which we have used in tutorial 3. You already know in the first semester also we have done overstrength omega. What is that? What is overstrength? We have used overstrength concept in first semester also. So what is this overstrength? Overstrength is nothing but the ratio of the yield strength divided by design strength. That we call overstrength. Design strength you will get from the code. Okay, and for RC structures, omega is approximately . So if I am plotting V versus delta for any building, it may be V versus delta rho. So whatever shear, base shear I have used in the design, the yielding will occur roughly at double. So in some of the questions, you have to first calculate VD from the code using whatever we discussed in the first semester. Okay, all of you know how to design using codes. IS 1893, you can calculate VD, and then VY you can simply take double of that. That's it. Okay. So now you can complete tutorial number 3. Any difficulty, we will discuss tomorrow. I am not going to cover any new topic tomorrow. We will only consider difficulties in tutorial number 3. Yes. Yes. Done. But in this case you can't. And not only roller, there are some things we do not allow a movement in the transfer. So we use the bridge because we can't move the transfer. The transfer direction is this big transfer direction, this is also good. This is also. Both hands are being supported. And isn't like